Hi, welcome to CSE351 Introduction to Data Science, and here we are looking at statistical significance. Okay, so this is again some difference between statisticians and computer science people. So whenever the statistician are looking at an observation, then they always worry about significance. So their primary concern whenever they look at some observation is that what is the significance of the observation that they are looking at. Whereas computer scientists, you may call them as data miners because they do this kind of work like statisticians, and a data scientist also fits in that a role. Our primary concern is to find whether the data is interesting or not. So a data scientist might think about the significance because data scientist is supposed to know more statistics than computer science. So you should know about significance tests and all. But as a computer scientist, if computer scientist is working on data mining project, then often they are excited about the observation, and they look at the interesting feature of the observation. If they are mining some pattern, they look at whether those patterns are interesting or not, the observation they have is interesting or not. They often ignore the notion of significance. So let's look into this significance, like what is it now. So it relates with the meaningfulness of the observation. Okay, so what happens is that whenever you're looking at an observation, how will you measure that whether this observation is significant or not? So computational analysis readily finds pattern and correlations in large data set. Good, that's what people do. But we don't have any but just looking at the pattern and the correlation and not finding out any significance is just useless. So let's try to find out, like, how will we evaluate the observation as significant or not. Okay, so we need to know that whether the pattern that we are finding out is significant or not. So what might happen is that, if you remember, in our previous discussion, we figured out that when the data set or the sample is really big, then even the small correlation that you find is meaningful, right? But we need to figure out, like, our data set is big, really big. We have a lot of samples, and we found out some correlation which is reasonable as per the standards, but is that significant or not, right? So this is the kind of answer that we are looking for in this lecture. Sufficiently strong correlation on the large data set may seem obviously significant, right? But we need to prove that it is significant from statistics point of view. So that's the goal of this lecture. Okay, so now let's change the role a little bit. We as computer science people, we are fascinated by data, and we have a lot of data. When we do some result, and when we find a pattern in a really huge data, we believe that what we have found is obviously significant, but that's not the case. So let's change the rule. Let's think about the statisticians, right, in a difficult domain, in a different domain, and try to understand how do they deal with the data. How is their data different from our data? Okay, and how carefully they get the information out of their data which they are given. So here we are looking at the case of the statisticians from medicine field. So you may call them as medical statisticians. So what they might be doing, let's say that they are evaluating some drug. So they have used two drugs, let's call them drug A and drug B, and they have some observation on the usage of drug A and drug B. And now they need to make a judgment that whether drug A is better or drug B is better, and look at the data. So pay attention to the sample size. So the result that we have in this medical statistics observation is that drug A cured 19 out of 34 patients, and drug B cured 14 out of 21 patients. Now, this statistician has to make a judgment about the drug. Is drug B better or drug A is better? Okay, so these kind of questions are um, difficult to answer because the data size is very small. It's not as big as we tend to handle. So you might wonder, like, why is this data so small? Why was this only tested on 34 or 21 patients? So for that you need to understand the domain. It's not easy to get a large number of patients because this is the question of their life and death, right? So it is about drug. You are trying a drug on patient, so there's a risk involved. The patient might lose the life. Okay, so these are very difficult experiments to conduct, and often the cost is pretty high. So the number of observations will be small, right? We won't have a very big data. So they need to decide, they need to make some judgment on this smaller data itself. So why is this important now, right? So kind of we understand that the data that these people will get would be comparatively smaller than the data people deal with in computer science. And then the other thing is that what is the deal? Okay, so how will the drug A being preferred over drug B reflect in the business? So assume that there's one company named A that has a drug A, and there's a company named B which has the drug B. So now, if the drug is being of company A is being approved by the FDA, then that will have a big implication on the business of the company A. Its stocks will rise, will go up. All right, so these things are big issues. Like, these are the questions of billions of dollars for each drug company, right? So these are very important decisions to be made by organization like FDA on the basis of the data that they have about the number of patients which were cured using drug A and the number of patients which were cured using drug B. Okay, so and these are the cases where the statistical test or statistical significance tests are very handy. All right, so that was about a different domain that which is from the medicine. We were trying to understand, like, how is the life for the researchers in medicine or statisticians in medicine, and why will this be helpful for us? Let's try to understand the same scenario in our domain, which is the data scientist domain or machine learning domain. So you might be looking at designing a model which is a classifier. So for that classifier building also, if you want to build a classifier, you may have to decide, like, which classifier is doing better. So assume that you have two classifiers that you have built. Let's call that classifier A and classifier B. So let me use pen for this discussion. All right, so we might have to deal with the similar kind of scenario as we saw in the previous slide, which was for medical statistician. Now let's assume that we are building a model which is a classifier. We have to make a decision about classifiers, and we have two classifiers, classifier A and classifier B. All right, and we are trying these classifiers on a data. So we are given a training data, we are learning our classifier, and we want to see the performance of the classifier on the test data. And now we have some result. The classifier A, its performance is accuracy, you can say, is 84%. All right, and classifier B is giving the performance as 86%. Right, now we need to decide, like, should we prefer A or should we prefer B? So if you totally disregard the significance, testing that we are about to learn, then you might pick B, right? Because the observation is that B is better than A, and this difference is 2% in the performance. But we need to think about this thing also, that this 2% performance improvement that we have in the classifier B, is that by chance, or is that by is that a genuine difference, or it is by just chance? So that's what we try to find out in significance testing. We would try to evaluate that the difference which we see in the performance of algorithm A and algorithm B for classification is genuine, or it is by chance. Alright, so here in this scenario also, the significance test that we'll be learning would be very handy. Okay, so that was about classifier. Let's also look at some so this same concept can be applied to a number of situations. So let's try to see what we have here. In building a classifier to distinguish between two classes, it pays to know whether the input variables show a real difference among classes. So here in the slide we have a different interpretation which can relate to what I told you right here. So assume that we are making some evaluation or observation where we have a number of features, right? Input variables. Let's suppose that we have input variables A and B, right? And you are making a classifier which is function of A and which is function of B. So this is classifier A. You may consider that as A is a classifier which is based on the attribute A or the variable A, and B is a classifier which is based on the other attribute which is B, and they are giving the same performance like 84% and 86%. Right now you need to evaluate that this difference that we are getting, is that real, or is that just by chance. Okay, so that's something we'll find out by the significance test in the classification domain. All right, so now let's look at a test which we might like to do, which is very general and that can be applied in a number of situations. So this test is called the t-test. All right, so the name of the test is right here, the t-test. And what does this test do? So we have different kinds of tests for different parameters. When you have to make a judgment about mean, right? So assume that you are given some population, and from those populations you have some samples, right? So let me make some example for you. Let's assume that this is population P1 and this is population P2. Okay, and from population P1 and P2 you have some samples. All right, so it had a lot of points. It's a very big number. So what we did some sample, and from that sampling we got some points out of P1. And similarly from the population P2, you can assume that these are the population of individuals, or men. Let's say these are men in Australia, and similarly you can say these are men in USA. Just coming up with an example. So what you did, you took a sample of men from USA, and you took a sample of men from this is from Australia, and then you had some sample of men from USA, and then you found the mean of their height. Okay, so this is mu1 and this is mu2. Now you want to say something about the difference in the mean, right? So whenever you have to make some judgment about the comparison of the mean of two samples from two different populations, then we will be using t-test. Okay, so if you are given some two samples, say sample 1 and sample 2, and you found their mean as mu1 and mu2, then whether this mean is coming out from one distribution or from different distribution. That's the kind of answer we'll get when we use t-test. Okay, so it will evaluate whether the population mean of two samples are different or not. Okay, so you got these two samples, and let's be ignorant of the fact that we have two samples in two populations inside, like P1 and P2. Just looking at the mean mu1 and mu2, which is coming out from the two samples S1 and S2, we will determine whether these two samples that we have S1 and S2, they are coming from the same population or from different populations. So that's kind of answer we will get by using t-test. Okay, so right here the question, the example that we have is different from what I came up with here, which is about the people from two countries, Australia and USA, and I'm thinking about their height. So let me erase that, and I'll stick to the other example that we have in our lecture, which is about the IQ. So assume that we have the IQ of 20 men and 20 women, and we want to evaluate whether there is any difference in their IQ or not, whether the difference that we find in their IQ, which is mean of the IQ, is significant or not. So that's the problem we are looking at. So given the sample of IQ of 20 men and 20 women, now we want to evaluate that are men smarter or women smarter, right? So what you will be doing, you will take the IQ of 20 men, you will compute the mean of men IQ, and similarly you will compute the mean of women IQ, and you want to see, like, is IQ of men higher or IQ of women is higher, and then you will evaluate that the difference that you are finding is that significant or not. So these kind of questions we look at when we do the statistical testing. And right here we are doing one instance of statistical testing, which is called the t-test. All right, okay. So the fact is that when you are given these two samples of 20 men and 20 women, it's highly likely that when you compute the sample mean, that means the mean of these two men and these 20 women, that the sample mean will be different. Okay, very highly likely. Now you need to evaluate that this difference that you're getting, is that by chance or is that genuine, right? So these kind of questions we answer, that the observation is by chance or it's genuine. All right, so let's try to understand a few aspects of the distribution before we get into the t-test. So for t-test we have an assumption that the distribution follows the samples that we have follows the normal distribution. So we will confine ourselves to the normal distributions here. So all the six plots that you have, three on the top right here, these three, and the three that you have in the bottom, these are all normal distribution. Now let's try to see, like, what is unique about these three and what's unique about uh, the the plots that we have in the bottom. So in this case, if you pay attention, then in all these three cases, the standard deviation of the curve is same, right? So the standard deviation of pink here, pink here, pink here is same. Similarly, the standard deviation of blue, blue, blue is same. Whereas if you look at the mean, right, this is a normal distribution which is totally described by two parameters, which are mu, that's the mean, and sigma, the standard deviation. So what is changing here in these three cases, if you compare, then that's the position of the mean, right? So you will have mu pink right here, and somewhere here you have mu blue, right? Mean of pink distribution and the mean of blue distribution. They are right here, but their standard deviation is same. Whereas if you look right here, then the mean is different for the pink, right? Mu p prime and mu blue prime. And right here again you can see that the mean has changed for these two distributions, right? So mu pink double prime and mu b double prime. So in these three plots that you see on the top, what has happened is that the mean is different. In the first case, we have the mean of the two distributions are pretty close, right? So that's the reason we have a very decent overlap between these two distributions, the distribution in pink and the distribution in blue. If you compare their mean, then these two means are pretty close, because of which you can see a very high overlap. Whereas in the second figure on the top, if you look at, then the mean have changed a little, have shifted a little bit compared to the first one, because of which the overlap that you see is a lot less than what you have on the left hand side. For the rightmost side of the top row, you can see even less overlap. That means the mean has further moved away. All right, fine. So that was the scenario where the standard deviation was same, but the mean was changing. So we started with the means very close, and then we kind of started moving the means a little bit, so that the overlap between these distributions reduced. Now what do we have in the bottom? So here, if you pay attention, then the mean is not changing. The mean of the two distribution is same. Right here, right here, right here, right here. Okay, similarly right here, 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 and mean means what you see on the x-axis, right? That's relative position is same. Whereas if you look at the standard deviation, of which you can also think in terms of variance or the spread, then the spread is changing. In the first one, we have a lot of spread, right? The highest spread we have is on the bottom row, leftmost side. If you move further in, then the spread is kind of reduced. So the standard deviation here is smaller than what you have on the left, and on the rightmost we have even the smallest standard deviation in the lower row. So here in this diagram, we are trying to understand the role of the mean and standard deviation when you have two distributions, right? So the point is, when you want to compare two distributions, then what would be the role of their corresponding mean and standard deviation? In the top row, our mean is changing, whereas the standard deviation remains the same. Whereas in case of the bottom row, our mean remains the same, but standard deviation is changing. All right. So if you got that intuition, then it's very easy to understand t-test. So what do we want to find out in the t-test? So whenever you have to make a judgment about the difference of the two means, right? So you want to find out, let's assume that we have a sample, x1 sample, and you have x2 sample. In x1 you can have x11, x12, up to x1n. These are the samples in x1. And for x2 you have x21, x22 goes on to x2. This was n1, n2. So in x1 sample you have n1 points, whereas in x2 sample you have n2 points. And now you want to find out the difference between x1 bar and x2 bar, which is the mean of x1 sample and the mean of x2 sample. Alright, so this difference would be significant. It will be more genuine, I will say, if all these 3 points apply. So let's try to understand these 3 points. When the mean difference is relatively large, okay, so yeah, the difference should be large, right? So if you go back here, we should have a situation like this. of these three cases, we want the situation like this one, where the difference between the mean is significantly large, right? Is relatively large, and the standard deviation are small enough. Let's go back. This scenario where the standard deviation is also smaller. We want minimum overlap between the two distributions, which will happen when the difference in the mean is relatively large and also the standard deviation is small enough. Okay, and the sample size is also large. Alright, so we are more confident making any statement about the sample statistics when we have a big sample size. Okay, so the bigger data set, bigger sample size is always a good news. So what happened, all these 3 points that you look right here was combined into a statistics which is called T statistics. And how is this T statistics formulated? You have, the mean x1 bar minus x2 bar divided by the variance of s1. Okay, s1 is squared, which you can say standard deviation of the samples in x1 is squared, divided by their number of samples in x1 plus the square of the standard deviation of the samples in x2 set divided by n2. Right, so if you look at it, then intuitively you will understand what we are trying to say. So we are saying that this value of t should be high. We want a high value of t. Now when will that be higher? That will be higher when your this difference is high, the numerator should be high, and the denominator should be low. Okay, this whole should be low. So higher higher numerator divided by a lower value of the denominator will give you a high value. Okay, so with that, let's try to dissect this denominator further and try to understand when will we have a higher value of the lower value of the denominator. So if you have n1 as high and n2 as high, then the higher value of the denominator will further get this value lower. So we need n1 to be higher, n2 to be higher, but s1 and s2 we want that to be lower. Alright, so this thing will make a lot of sense once you write this expression for t and try to understand. And it's very intuitive and it's kind of capturing all the points that we need to have in the t-test. We want the higher difference in mean, we want the lower value of the standard deviation, and then we want the sample size to be large. Okay, so that's what we have in the t statistics. So the same kind of information you'll get right here also. You have low variability. So these are 3 cases where you are looking at the low variability, standard deviation or the variance is very small. Here you have a medium one, and in the bottom one case you have the highest variability. Alright, so now let's look at why these significance tests work. What is there behind these formulations? Now to us actually with our intention here is totally different. This is a course which is not on statistics, so we will not get too much deep into these formulations and these testings. We just want to get some understanding of what these tests do. So to us it might look like opaque. We may not know what is going on inside these tests, right? But we should understand like what these tests are trying to do. Not knowing the details about the expressions, like how did they come to these expressions, and probably not even doing any t-test in CSE351, but having some understanding of these approaches, like what do we try to do when we are doing t-test. Okay, so why do these works? Because these are based on the probabilities of the samples, and these are based on some assumptions about the distributions, and these are based on the understanding of mean and standard deviation, and which we kind of saw right here. And intuitively we can see that all these factors are playing the role in the expression of t, and that's how we are computing t. So for that reason these things do work. Okay, so uh, that's all right. It says that we kind of try to find out the probability of distribution given the data. So this is not very important, you can ignore this point. All right, so there's one more thing which I don't have in the slide. So you might wonder, like, what do we do when we find out this t statistics? What happens next? So when you find out a t statistics, then that will be a value, right? So assume that you computed a t, and now you want to say that whether this difference is significant or not. So what you need to do later is that you need to look up a table, right? So this is something I was missing out. So the value that you got right here, you need to compare that value with the standard value which will be available to you on the table, and you will see that whether the value that you're getting here is comparable to the value that you have in the table. Okay, and this value should be compared to the values that you have in the t-test, in the t-table, and you will use some significance value of alpha, and you will use some degree of freedom. And so the degree of freedom that you have, degree of freedom depends on the number of samples minus 1. So these two features you will use, and you will find out the corresponding value of t, and you will compare that t with the value that you'll compute the value that you find on the table with what you compute right here, and you will make your decision on the basis of that, and you will see whether your test is significant or not. All right. So let's look at another test which is called the Kolmogorov-Smirnov test. So this test is also there to compare two distributions, but it works slightly differently compared to the t-test. So the purpose of this test is to compare any two distributions which are given to you, and for this comparison it works on the cumulative distribution function, right? So if you pay attention to this plot that we have right here, then what it tries to do is that if you give if you provide two distributions which are probability distributions, then it will first compute the cumulative probability distribution, right? So I hope that you understand what is cumulative distribution function. If not, then please go back and refer to the lecture which was on cumulative distribution function, and then it will make more sense. So the cumulative distribution function gives you an idea about the probability, right? So if I look at the cumulative distribution function which is in red, and if you pick any point here, right, so it will give you the probability of x being equal to 0 or less. So this much is the cumulative probability till this point, right? And it's a cumulative function that monotonically increases and it reaches 1. Okay, so that's how we define cumulative probability distribution, and this is derived from probability distribution function. So for a KS test, which is Kolmogorov-Smirnov test, you need to have the cumulative distributions of the two distributions that you want to compare. Okay, and then on the basis of these two distributions that you have, then you look at this value which is called d and n dash and prime. So let's try to understand. Okay, so this test measures whether two samples, it's kind of doing the same thing. It measures whether the two samples are drawn from the same distribution or not. Alright, so you'll be always given samples, all right, and on the basis of the sample you'll do some statistics, and then once you have the statistics on the sample, then you will ask this question that these samples which are given to me, do they belong to two different populations, or they are coming from the same population. So that's kind of answer we are looking for. And here when the two samples are given to us, then what we do, we find out the maximum difference in their cumulative distribution function. Okay, and how do we find that? Let's see, if we are given two samples and we computed that their cumulative distribution function, then one is in red, the other one is in blue, then we try to find out the value of x where their distance in y, which is the probability here, is maximum. Alright, so we have this value of x right here, for which the distance in y, which is the probability, is maximum. Alright, so this is something we try to find out, and that's how we compute whether this is different or not. Alright, so similar to the concept of t-test, but here in t-test we were comparing the mean of two samples, but here we are comparing the cumulative distribution function, and there we are finding out 2 points. We are finding out a value of x for which the difference between these two cumulative distribution function is maximum. So that's what we have here. D n n prime that you get here is equal to finding out the x which gives you the maximum value. What is it? f1n x and f2n prime x. This f1n x corresponds to you can pick any one. You can pick f1 as the red one, then f2 would be blue, or the vice versa. So you compute this distance between the maximum distance between the two CDF at a specific point x, which gives this maximum value. And then once this distance is computed, then you compare this, right? So you compare this with some value like C alpha. For this C alpha you have to look at the table. So you will look at the table with alpha value, which is a significance value. Often this significance value is used as 0.05. So you will have to find out that value from the table, and then you know n and n1, which is the sample size. N is the sample size for f1 CDF, and prime is the sample size of f2 CDF, and then you put that in this expression, which is square root of n1 n plus n prime divided by n into n prime. And then you see that whether this distance that you see here is more than what you have on the right hand side. Only when this distance is more than what you have on the right hand side, you will say that the difference between these two distributions is significant. And when the difference between these two CDFs are significant, then that means that these samples that we are getting are probably coming from two different populations. Okay, all right. So let's move on and try to understand that why is this KS test so important? Is there anything different than what we have done? Can we do something more than what we have done right here? So the answer to that is yes. This KS test is in fact very useful. We can also test this. We can also make use of KS test in other situations. So let's look at the situation number 1. So in situation number 1, if you are looking at, so here we have two distributions. Alright, so if you pay attention, then the blue curve that you have is very close to a diagonal line here. Right, some variation, right? It's not pretty straight, but it's still kind of there on the diagonal line. So which means that you have a kind of linear linearly increasing, linearly monotonically increasing CDF, which means that your probability distribution function, that you have for this blue CDF is uniform. Alright, so uniform probability distribution is what we have here for blue. Whereas for this red CDF that you have, this is normal. Right, so now if you are given some samples, one sample belonging to the uniform distribution and the other sample corresponding to the normal distribution. So red is the CDF for normal distribution, cumulative distribution function, and the blue one that you have is uniform CDF. And if you compute your case distance here, then you know the intuition behind that. We are looking for the x where the difference in y, which is the probability, is maximum. So you can see that we have a reasonably high difference in these two CDFs, which is giving us an idea that these two samples that we have are not coming from the same distribution, right? So we are kind of doing this experiment to check whether KS does its job or not, right? And you can easily see that KS is doing a decent job because of the huge difference that you see here. It's giving an indication that the samples which are represented by blue CDF and the samples which are represented by the red CDF are in fact coming from two different populations. One population corresponds to the normal probability distribution function, whereas the other one corresponds to the uniform probability distribution. So that was one scenario where you can check whether the samples are coming from the same distribution or not. Now in the second case that you have here is even more interesting. Second case corresponds to the situation where you have two samples, and these two samples are basically coming from the same population, right? So the red curve is also the red CDF is normal, the blue CDF is also normal, and the fact that these two are so close is giving a hint that these two samples are probably coming from the same population, which is distributed with the normal distribution, and probably it has the same parameter as we have for the blue one. So that means that this closeness between these two CDF means that these two samples are coming from the same normal distribution. Okay, and there's another application which I should add as point 3 of another application of the case test is that when you are given a data which is bell shaped and you are not sure whether the bell shaped curve that you have is normal or not. So let me put that here. Testing for normality, right? So we already have normality testing. What does that mean? Normality testing means that if you're given a bell curve, you're not sure whether the bell curve is normal or not. So what you should be doing is that from the bell curve that you have, if you know its mean and standard deviation which you can compute, then using that you can normally generate some random samples. Alright, so assume that using the mean and standard deviation from the input bell curve that you had, you randomly generated the normal CDF, which is red. Normal CDF, which is red in color, is the one that you have sampled, right? You sampled as normal. There are some ways in which you can randomly generate some data. So what you did, you randomly sampled using normal distribution this curve that you have in the red. Now what you can do, you already have the data, and this is some bell curves, bell shaped distribution, and you don't know that whether this bell shaped distribution that is given to us is normal or not. So what you will do is, to this given input which you need to judge whether it is normal or not, you will find its case distance, or you'll do its case test on the normal distribution that you just generated by randomly sampling the data using the normal distribution. Okay, so that's another application of the KS test, which is about testing the normality of a distribution or a sample. Sample is given to you that looks like a bell shape, but you're not sure whether this is normal or not. So what to do? First, generate a normal distribution based on the parameter of the bell curve that you have, and then do this KS test on your sample with the distribution that you have obtained, the normal distribution you obtained. Alright, so I'm not sure whether you're following me. I will highly recommend that you should read the textbook for this thing. Don't hesitate in asking me for questions if you have any on these. Alright, so now let's move on to another concept which is called Bonferroni correction. So the Bonferroni correction is given for the reason that sometimes people do cheating. So what do? They do multiple tests. They try multiple hypotheses using just one significance value like 0.05, which we denote as alpha. Now this alpha, which is the significance value of 0.05, is good if you are doing one hypothesis testing only. If you are doing just one test, which is about the correlation of any two attributes or any two fields you want to correlate, and you want to see whether this correlation is significant or not, then for one test, one hypothesis test, using the alpha as 0.05, which is equivalent to 1 by 20 probability, is fine. But if for some reason you're trying a lot of hypotheses, right, you are trying to correlate multiple fields in one experiment, then probably this value of 0.05 is not good enough. So if you are trying an hypothesis, right, and hypothesis means if you are doing n test, not one, n test, then for significance value, what you should be doing, you should consider alpha by n, not just alpha. Alright, and if you're doing an hypothesis testing and for all you're just taking alpha, then that is a cheating. Alright, so that is a correction which has been suggested, and this correction is called Bonferroni correction. And what it says that if you're testing an hypothesis, right, then for an hypothesis testing, you should consider alpha by n as your confidence level or significance level, not alpha. So the reason why this is important is that at times what people do in research, they continue doing experiments, right? So as an example, they are generating some sample and then they are checking whether that sample is significant or not, whether that observation is significant or not. And if that fails in the first attempt, they'll try again, they'll try again. So they continue doing it, and when they get the value which is significant, they report it. So in the process, what they do is they might try, say, hundreds of times. So if you are doing it n is equal to 100 times, right, assume that you tried the same experiment 100 times, then that means the number of hypotheses that you tried is 100. So alpha being 0.05 is not good in this case, right? Because if you're trying it 100 times, definitely you'll get some result which will be significant. So what you should be doing, rather than using alpha is equal to 0.05, you should try alpha as 0.05 divided by 100. So that's the correction which has been proposed by Bonferroni. Okay, and this is something you need to keep in mind. I know that this is too much of stuff because we are not getting too much into the depth. So I will just recommend you to remember these expressions and some intuition behind it. So what's the intuition? When you have when you're testing multiple hypotheses, that means n hypotheses, then just alpha is not sufficient. You need to be more strict, and you should change the significance value to alpha by n. Just divide that by n. Alright, so let's move on. And there you'll find an interesting plot right here, which kind of relates to Bonferroni correction discussion. So what happened actually, people were doing some research, and in the research they were trying to find out the correlation between different attributes, different fields, different measures. And what they found very strong correlation between the PhD student graduating and the revenue which is being generated by Arcades. So Arcades is a gaming company. So what happened? A strong correlation was found between the computer science PhD graduate that were produced and the revenue that was being generated by arcades games. So it is kind of and the value was very high. I think it is some 90, yeah, it's 98.51% correlation, which is pretty high, and which is giving an indication that there is a very strong correlation between the CS PhD students graduating and the revenue which is being generated by the arcade. Right, so this is probably the result where multiple hypotheses were tried out, and the alpha was kept as 0.05, so which is spurious result, right? So these things would be avoided when you are careful about the choice of alpha. It should be alpha by n, because you are doing n multiple hypothesis testing in one go. Okay, so now uh, let's try to understand like what significance testing gives us. So when you do a significance test and the result is in your favor, then it means that whatever difference that you're finding out by your using your significance test is genuine. It's not there because of a chance. Alright, so that's what significance test gives us. And what might happen is that as you looked at the expression for t-test, I'll take you back to the t-test. So here it is possible to get the decent significance value, which will say that the difference in the mean that you're getting is significant. It's not there because of a chance, right? So it's genuine. So this value that you're looking at is controlled by the sample size, right? N1 and N2. So if you have really big sample size, then even with the smaller value of this difference between x1 and x1 bar and x2 bar, you will be able to get a reasonable t value which will work in your favor, right? So although the significance test is saying that the difference that you're finding out is genuine, it's not there by accident or by chance, this is not this is not in any way giving us the measurement of the difference between the distribution, right? So this thing is important for us to understand. The significance measure is measuring the confidence, right? The confidence that there is a difference between the distribution, but it says nothing about the magnitude of the difference, right? Difference is there and the difference is significant. That's what significance test will say. Okay, it will say that whatever difference that you're looking at, which could be 0.2, that's the difference you're getting, and this is genuine. That's what significance test will say. But it will not say anything about the magnitude, like is it sufficient, is the difference that you're looking at, is that an important difference or not, right? So that answer significance test does not provide. So this fact about the magnitude of the difference is captured in effect size. Alright, so whenever you see the keyword effect size, then that means you are focusing on the difference of the magnitude, right? Is the difference sufficient or not? So you might not be happy with the difference 0.2, right? 0.2 is genuine, that's what you figured out from a statistical test, but this might be a very small difference. You may like a difference to be 0.5. All right, so sometimes even the size is important, the effect size is also important. Okay, so let's look at that thing. So for effect size we have some measures. So what are these measures? So these are some recommendations, like when will you consider the difference between the mean, right? So let's start with the difference in the mean, because we started with the t-test. Now when will you say that the difference in the mean is important, right? So importance or the magnitude, right? So importance, the difference is important or not. I'll say that 0.5 difference is important. Okay, it's significant and important. This is significant but probably not important because this is small. Okay, so for the mean difference, we have this formulation given by Cohen's. So this is D, which is computed as the difference between these means that you have divided by standard deviation. So here you can use sigma or sigma prime, any one of that you can use. Now when you computed D, which is the difference between these means divided by standard deviation, you will say that the effect size is small if it is just greater than 0.2, and you'll say the effect size is medium if it is greater than 0.5, and you will say that the effect size is large when it is greater than 0.8, right? So there's another measure we have, which is the effect size, and this effect size will highlight the difference in the measure, right? That will highlight the magnitude of the difference. So magnitude of the difference between two means should be greater than 0.5 if you want to have the medium effect size, and if you want to have a larger effect size, then the difference in the mean should be 0.8 or higher, more than 0.8. And at the same time, uh, we should have high effect size, and we should also have the significant difference. So significance is important. We cannot throw out significance. Significant and then higher effect size. That's what we need ideally. Okay, so we have seen the case with the mean, like how do we compute the effect size from mean. Let's look at the other cases like Pearson correlation. So we have already looked at the Pearson correlation coefficient, and we know that its value is between -1 and 1. So for that, when will you consider that the Pearson correlation between the two variables is of a large effect, right? So we have the same measures. If you look at the measures that we had for mean, we have the similar kind of value for the Pearson correlation also. We will say it will have a small effect if it starts from 0.2. So it's in between 0.2 and 5. We'll consider that as small effect, and medium effect would be something at the value of 0.5, and the larger effect would start at 0.8. Okay, so these are the same values as we had for Cohen's, which is the mean difference. Okay, so now we have the overlap, right? So how will you say that the overlap between the two distribution is of a small effect, medium effect, or large effect? So now you look at the overlap between the two distribution, and you'll say that it will have small effects when you have only 53% of overlap. You'll have medium effect when those two distributions are overlapping by 67%, and larger effect if you have that as 85%, excuse me, or higher. Okay, good. Now there are these concerns, right? If you have never done the statistical testing before, and you never had a course in statistics that talked about significance testing, then probably you might be a little confused, and I won't be surprised, because we are not discussing in the detail which we need to do, but then it will be beyond the scope of CSE351. It should be covered in more detail in some statistics course. Now the message that I want to give you about this thing is that these things are little involved. You need to have a very good understanding of some distributions. So for t-test we make the assumption that the means that we are comparing are coming from normal distribution, and there are other subtleties as well, right? So we have many subtleties. We should decide like whether it's one-sided test, it's two-sided test, right? And you need to look at the table and you need to come up out with the values and then decide whether this is significant or not. So there's another approach for statistical testing which is very popular between the data scientists and which is idiot proof, right, which is computationally idiot proof, is called the permutation test. Okay, and it's more general as well, and it's very easy to use. So let's look at that last significance testing, which is called permutation test. So what do we do for permutation test? Uh, okay, so as the name suggests, which is permutation, we do the shuffling of the data. Alright, so let me read it and then I'll explain to you what do we do. In your if your hypothesis is true, then randomly shuffled data set would not look like real data. Okay, so the ranking of the real test statistics among this. Okay, this is something I'll explain when I'm giving you the example. You need the statistics on your model which you believe is interesting. Okay, so the point is that when you're doing permutation tests, you should have something in your mind, like what is it that you are evaluating. So for the example that we are looking at the height. Okay, so here we are looking at the height, and the height, the mean of the height is being evaluated for gender. So we want to make a we want to analyze this thing, like, is there any difference in the height of the male versus the height of the female. So that's kind of thing we are looking at. So you need a statistics, right? So the statistics for our case is mu of height. Alright, so we are looking at the mean of the height, right? So that's the statistics we want to evaluate, and we have two samples here. We have the heights for females and the height for the male. So what you are looking at in the top is the height of the samples for females, and then in the bottom you have the height of the males. And we are about to do the permutation test, which is very simple. So what do we do here? We keep all the females sample height in the top and the males in the bottom, right? So you can change the order, but in this example we have the height of the females in the top and the height of males in the bottom. And you must have figured it out that this is stored in the ascending order, right? So we have sorted it out. We have sorted it out in such a way that the height of this sample of the female is in ascending order, and similarly the height sample of the males is also in the ascending order. So if you pay attention to this data now, then it is kind of giving us a hint that the mean height, the average height of the female, that should be somewhere right here, is less than the mean height of the male, right? Which is reasonable, right? So looking at it as a computer scientist, as a data miner, someone might in excitement claim that the average height of males is more than the average height of female. But as a data scientist, we need to do the test as well. We cannot say that that is the case. We need to do some significance testing. So now how do we do this permutation test on this sample? So what is done here in the permutation test, we will keep these labels right here. The label red means all the females, this all red means females, and all blue here means male. So what is done in permutation testing, these heights that you have, is randomly shuffled. Okay, so these values will remain same, but these values would be randomly shuffled. So what will happen, probably this height right here that you have, when it is shuffled, it might go here. Alright, similarly these heights that you have being shuffled, some of these heights might be assigned to ladies right here. Okay, so when you are only shuffling, see, pay attention, we are not shuffling this section, right? This much portion, which means the females, is right here, right? We did not change that. So we are not moving the male and female, we are keeping them as they were. What we are doing, we are only shuffling the values of the height. So when you shuffle the values of the height, then it looks something like this, right? So probably I created a lot of clutter, so let me clean that up. Okay, I'm cleaning all the clutter. I hope even without the clutter you will understand what we have here, what I'm trying to explain. Okay, so don't change these ladies that you have here. They should stay here. The gents, they should stay here in that order. What we are doing in permutation, we are only shuffling these values. So by that shuffling, what will happen, some heights of the male would be assigned to some female, and similarly the height of some females would be assigned to some males, and in this set also the males, they will exchange their heights, and the females, they will exchange their heights. So this is a shuffling process where we are shuffling the heights only. The relative position or the position of male and female remains the same. Now once you have done this shuffling thing, what we do the sorting between, uh, we do the individual sorting in male as well as female, right? So after doing this shuffling, you will get a new sorting here. Okay, sorting of the heights, which is being reassigned. Now we have a different height being assigned to male and female. And after this permutation and sorting, if you look at the mean, then you will see that the mean of the female sample and the male sample's height looks a lot different than what we had initially. Okay, so this is kind of giving us a hint that in fact there is a difference in the height of the male and female. So that is the intuition behind the permutation test. Okay, shuffle the heights. We are looking at the example of the height. The same can be applied for other case also. First, for each class, that means for female and for male, first sort their heights right here. Okay, so that's what we have done. First sort their heights. Remind me later, sorry about that. So we sorted the heights for females, we sorted the heights for male, we looked at their mean, we got some value of the mean, we will find the difference between the mean, okay, which is something I think which will come in the next slide. And once we have done that, we noted the mean for female, we noted the mean for male, and then we shuffled these values. We did not shuffle these people like male and female, we just shuffled these values, and we have got a different distribution right here. Now for that again we'll do the same kind of sorting between the males and females, males here, females here, and we got a different distribution. This is shuffled distribution. And now in the shuffled distribution again, you will compute the mean for the female population and the mean for male population. And now you will again see the difference. Like, is this the difference same as the one we had in initially, right? So that difference will determine whether the shuffling did anything or not. So shuffling will kind of give you some idea that whether the difference in the height is genuine or not. It's a different way of doing the same kind of statistical testing. So what you will do here, let's try to understand this plot. What you did here, you did just one random shuffling. You need to do this shuffling multiple times, 1,000 times you need to do it. This is just one step where you kind of shuffled and then rearranged and found out the mean. You need to do that. What you need to do that permutation test. 1,000 times or even more than 1,000 times. So what happened, let me write these things because that is needed. Mu female. Alright, this is the real mu female and mu male, right? So assuming that when you compute the mean of the height of the females, you got this value, and similarly the mean of the height of males, you got this value. And after first shuffling, what you have got, you got this thing, right? Somewhere here, I'm not sure whether I'm putting that in the mirror at the right position. Mu s for suffered, mu s1 I should say, mu s1, and this is for female. Sorry about that. Okay, this is female. Mu s1 because that is suffering 1 of female, and similarly you will find out mu suffering s1 of male, right? So this was in the first permutation. You'll do multiple permutation, you'll do thousands of these, right? And what you have to do for each of these sortings that you get, you will compute mu of m minus mu of female, the difference in the mean. Similarly, you will do mu s1m minus mu of s1 female. Now out of these 100 permutations that you're doing, you'll get these values, right? You'll get these 1,000 values. Then what you do, you will do a histogram. So this histogram that you are looking at is on mu of I means you are doing it 1,000 times, of male minus mu si of female, and this you have 1,000 such records or maybe more, and then you plot a histogram. Alright, so this histogram is kind of telling you that how many times the difference was 0, how many times the difference was -2, how many times you had the difference as this one. So this is the histogram that you're looking at is the histogram of this difference that you are obtaining after doing the permutations, and you are doing that 1,000 times. Now you would wonder, like, what is this line here? Now this line that you're looking here, it is representing the original mu of m minus mu of f. Alright, so it depends, right? The mu m minus mu f, which you have as the original difference in the mean of male and female, may lie anywhere. It can be in the middle of this histogram, and the histogram corresponds to the shuffled difference between the mean, or it can be in the extreme like this, right? So scenario is 1 or 2. Now we need to understand, like, which scenario means what. What is the meaning of scenario 1 and what is the meaning of scenario 2? In the case of scenario 1, what has happened is that the real difference that you found between male and female is much higher. This would be mu of male minus mu of female is much higher than what you'd have got in the random shuffling, right? So all these instances that you have here, they corresponds to the difference in the mean of males versus females after you did the shuffling, right? So that means when you're doing shuffling anyway, you are messing up with the order of the heights of males and females. So this means that this kind of a result where your mu m minus mu f is far away from the histogram that you got for the difference, means that the difference in the height, which we are capturing by mu, is significant. Why is this significant? Because the real difference that we have is far away from the difference that you are getting by doing the shuffling. Whereas a case like this, where the mu m minus mu f, which was the original difference in the mean of the height of male and female, is somewhere in the middle of the histogram, says that this is not significant. What is this? The difference of the height of the male and female is not significant because this is lying somewhere in the histogram which we have generated using the random shuffling of the heights between males and females. Alright, so this is very intuitive to do and very much self-explanatory, like the logic behind the permutation significance testing. Alright, so now the last point that we have is about the permutation test, like why we should be careful about permutation test. Already communicated this thing to you that this is simpler than the other significant test and is more intuitive and is something which is very popular in data scientists, and it is idiot proof. Yeah, it is idiot proof. I like this thing, okay. Now there are a few things that we should be mindful of. Let me put the pen right here. Okay, so permutation test gives you the probability of your data given your hypothesis, right? So this is the way we are computing the permutation test. It is kind of evaluating the probability of the data given your hypothesis, right? Which is in a way opposite to the existing hypothesis testing, where we find the probability of the hypothesis given the data, right? So it is kind of a counter, intuitive, I will say, to the notion that we have in the traditional significance testing. Alright, so that's it. Actually, I don't want to cover too much on statistical testing. I believe what we covered in this lecture gives you some intuition behind statistical testing. Please don't hesitate in reaching out to me, because I believe this is little intense, and yeah, read the textbook and anyway reach out to me with your questions. I'll be happy to help you. Thank you so much, and I'll see you in the next video lecture.